Hello everybody, welcome to Science, Technology and History Explained. Today we are looking into the exciting world of fusion. How can we explain it simply? What happens inside the sun? And how could we harness the power similar to the sun's core on Earth? Is that even possible? So let's take a look. Before we start, I think we need a matter fundamentals one-on-one, how it all works. Basically, matter is composed of atoms. Atoms, they have a nucleus where there are protons with positive charge and neutrons with neutral charge. Around the nucleus, we have electrons spinning around, and they have a negative charge. The number of protons determines the type of the atom. It could be carbon, oxygen, iron, uranium, hydrogen. Here I'm showing you hydrogen. It has only one proton. Helium has two protons. Carbon has 6 protons here. The number of neutrons can vary a little bit, and it doesn't really change what the type of atom is. For example, hydrogen could also have a neutron, then we call it something else. We call it deuterium. Helium could have one less neutron, for example. Carbon, I'm showing you carbon 12 isotope. This is a stable one. If you have 2 more neutrons, it's carbon 14. It's radioactive and it's not really stable, but it was using carbon dating, but it's still carbon. So, and if we stay, of course, when you see something like this, if we really could look how atoms would look like, I think we'll be surprised, because it will not be nicely spherical particles that just spin around each other and orbit each other like planets and suns. The reality is much more complex than this, but simple model like this help us explain what happens, and is a good visualization for us to try to understand what's happening. And basically, if we are sticking, if we don't dig too much into the nucleus and we're just standing around the electronic configuration and how those interact, then we're in the nice realm of chemistry. I'm a chemical engineer, so this is what I really enjoy looking at. If we move into the nucleus, we're coming into the world of nuclear physics. If we zoom completely inside this nucleus and these particles and look at how electrons really behave, then we are starting to come in the realm of quantum mechanics, which everything becomes much more complicated. So with this matter 101 out of the way, what is then fusion? So basically fusion is a process where lighter elements, smaller nuclei, are fused together to larger nuclei, and large energy can be released in this way. Typically fusion can happen with the lighter elements on the periodic table. You can't, it's very difficult to fuse, let's say, big elements. Here you don't get energy if you fuse big elements, as we saw in the nuclear power. I showed you, for example, some of these radioactive materials can be split into smaller ones, releasing a lot of energy, but the smaller elements can be fused together to generate a lot of energy. But it's not very easy to accomplish fusion. For example, if we have 2 protons, this would be a nucleus. The simplest nucleus is just 1 proton from a hydrogen. If we try to push them together, because both are positively charged, they will have a strong repulsive electromagnetic force, like if we try to force 2 magnets of the same pole against each other. But if we somehow manage to bring them very close together, then the nuclear force, the strong nuclear force, takes over and attracts the protons to each other. But in order for the distance to be closed and to have sufficient energy to come close so they can fuse together, very high temperatures and pressures are needed. We're talking millions of degrees of temperature and very high amounts of pressures. But when we can accomplish this fusion, typically massive amounts of energy are released. So let's first visit the most important fusion reactor that's really behind everything on Earth, all the life and basically all energy on our planet. And of course, this fusion reactor is the sun. All stars are basically huge fusion reactors. If we cut a section of our sun, a huge ball, largely consisting of hydrogen 75% and helium around 25%, something like this, mostly hydrogen. If we drill a hole in the middle, in the core, the temperature in the core is around 15 million degrees centigrade, and the pressure from all the weight of the star is enormous. And the fusion reactions that happen in the core of the sun is basically that in multiple step, 4 protons, that's basically a simple hydrogen nucleus, becomes one helium nucleus. This happens in several steps. There is some neutrons become let's say some protons become neutrons, and then for each step a lot of energy is released as gamma rays that come out of the sun and are emitted, for example, to end as visible light to our planet. But if we look at the basics here, the mass of the 4 protons that go into the reaction is this 6.691, and now we have to be really careful with the decimals here. We can't just truncate these numbers. This is how many kilos. It's very little amount. This has 27 zeros in front of this, but the mass of 4 protons is 6.691. The mass of one helium nucleus is 6.647. So if you see here, there is some mass missing in the decimals, 0.046. So 0.7% of the mass, original mass of the protons, has somehow disappeared. This is because the helium nucleus is more stable and more energy efficient way to store protons and neutrons compared to just having the protons by themselves. So this mass has been basically transformed into emitted energy, and we use the popular formula: energy is mc squared. For all the mass has been missed, has been transformed to energy. And if we look at this energy density comparison for fusion, if we theoretically could take a kilogram of hydrogen and just fuse it to helium nucleus using the process in the sun, we would be generating a whopping 630 terajoules per kilogram. Compared to fission in the nuclear, if we compare to pure uranium-235, which basically doesn't exist, it's 7-8 times more energy that we can release with fusing hydrogen than making fission of pure uranium-235. And if we compare to something like combustion, just burning some fuels and releasing some chemical energy, here we're not messing with the nucleus, we are still staying on the chemical side of things. Coal, for example, has 30 megajoules per kilo. If we burn hydrogen with oxygen, we get 120 megajoules per kilo. So this is orders of magnitude lower than what we get from fusion. So 1 kilogram of hydrogen fused is corresponding to burning 21,000 tons of coal. So it's like immense amounts of energy stored when we make fusion. And the fusion energy in the sun will allow it to live for around 10 billion years. It's already been operating for 4.5 billion years with fusion in its core. It has half of it left in the core to burn before bad things start to happen with our sun. But if all the hydrogen in the sun was combusted and just burned with oxygen, where previously people thought the sun was basically on fire, and it's not, it has fusion and there is no oxygen on the sun. If we only use the chemical energy of hydrogen to power the sun, the hydrogen would have been depleted on the sun after 10,000 years. So it's the 10 billion years or 10,000 years. This is the order of magnitude that fusion energy is compared to chemical just combustion energy. And now the question comes, can we build fusion power on Earth? Could we utilize the same processes on this planet where we don't have 15 million degrees and immense pressures? There are a lot of issues for sure. Basically, no material can withstand the temperatures that are required to start the fusion. There is nothing you can't have a container and keep 15 million degree hot mass that takes the form of plasma. You need to somehow contain the plasma in magnetic fields or something like this to avoid it touching something. And it turns out that this proton-proton process that we saw that the sun is using requires too high temperatures and energies to be feasible as a first step for us to make fusion power. So what we typically, when we are doing fusion on planet Earth in experimental reactors, typically we're using some heavier elements, deuterium and tritium nuclei. This fusion is investigating. It releases half the amount of the energy of proton-proton, but still it's really a huge amount. And what are deuterium and tritium? Deuterium is basically a hydrogen where the nucleus doesn't only include a proton, it also has a neutron. This exists naturally if we take, for example, water. Most of the hydrogen atoms in water would be normal hydrogen that only has the proton, but around 0.015% of the hydrogen in water, for example, would be deuterium, this type here. But we also need tritium. Tritium is also a hydrogen type, but in the nucleus we have one proton and two neutrons, and this doesn't really exist in any significant amounts on Earth. This could be a byproduct of nuclear power plants where water is bombarded with some neutrons or lithium or something else happens, but we need to somehow make this reaction, and still it requires very high temperatures, and then we could be harnessing some energy here. And if we look at the fusion reactors, the experimental ones or bigger ones that have been built, they are very complex machinery. We need very strong magnetic fields, as we said, to keep the very hot plasma of the deuterium and the tritium inside that will be fused. We need to heat everything up. We need to keep it contained. And this is how it looks. So this is a fusion reactor from Korea, and it's very difficult to operate this reaction in a way that you are receiving net energy coming out, because there is so much energy required to keep the magnetic fields and to heat up everything. So if we look at the different types and the progress of fusion over time, this is basically how the evolution has gone, where we are seeing more and more, let's say, more and more energy has been emitted or taken out of fusion. But this is the magical line where you are getting more energy out of your reactor than you're putting in to start the reactions. And basically, not many things are close. The tokamak type reactor could be quite close, but still far from operating. And here are some planned, and hopefully in the future we can get some fields where we can operate fusion that gives a net gain of energy. So it's really a complex a reaction to build something commercial in the current days. But is there any fusion power working on Earth? Unfortunately, the answer is yes, because we have weaponized it. And basically, when we are talking about hydrogen bombs, these are utilizing fission and fusion. So fission, the splitting of heavier elements like uranium, we're having a charge of weapons grade radioactive materials that initiate the fission. This creates a very high energy and pressures and temperatures, and this is enough to start the fusion of hydrogen, and we get a huge amount of energy released in one go. And this is not a very good way to do fusion, but unfortunately it's easier to make destructive powers than harnessing peaceful power of fusion. So this concludes the video. I hope it gave you a bit of background of fusion and the world of nuclear physics. It's a complex topic, and I think for me it's really amazing to see how small differences in the weight of helium and hydrogen is what really powers everything. Without it, we wouldn't have suns or stars or life or planets orbiting them, and there would be no light in the universe. So this concludes the video. Let me know your comments, and please press like and subscribe to the channel, where I hope to bring you more videos about science, technology, and history explained. And with these words, we're signing out. Stay safe out there, and bye-bye.